All right, so we're gonna start talking about what I just said, section 34. So if you think about it, this is kind of like this is like really our second section into the module. So like K nearest neighbors, which is I think is relatively like conceptually understandable. You're like, okay, like you basically just need to see who's nearby. So the next kind of like I think classically like when people say like supervised learning, which classification, basically we have our labels and everything like that. The classic one usually is decision trees. And that's because decision trees are really powerful, but also like relatively simple to understand. K-nearest neighbors, I think is relatively simple, but it's actually kind of not used as much in practice just because you have to store all the information and this becomes a little more intensive for most real world applications. But decision trees can actually do a pretty decent job. We will talk about a little bit, or I will mention right now, is that there are some issues with decision trees. One big issue is that they tend to overfit like a lot, which will lead us into the next time when we talk about ensemble methods, where essentially we'll use decision trees and other methods to basically compensate for that tendency to overfit. Okay, so let me go ahead and start sharing my screen. Let's see here. And yeah, I think I keep mentioning this. I think it's because I have a lot of improvements on this particular like module, but I kind of keep updating the repo. So to kind of know that, I think I literally just put a merge just like today. So if you're kind of using that fork, just know that it might look a little different. Okay. So just kind of going through like our first initial, decision tree intro. I like to kind of represent it with this little game. So it's called Inca Nader. You might have played this. Like I remember playing this back, like, I don't know, when I was like in middle school, like on the computer kind of deal. And basically it's 20 questions. So last time I did this, I actually turned out like it like crashed or something, did something weird. So basically it's just gonna ask a bunch of questions and kind of guess what is the thing that you're doing. So in this case, I'm just going to pick like something that we kind of probably all know is Mickey Mouse. It's pretty universal. So we'll pretend Mickey Mouse and they're trying to guess, who this person is, and we know it's Mickey Mouse. So we'll kind of go through it. Is your character real? No, Mickey Mouse is not real. Is your character from a Japanese anime? No, it is not. At least I don't think Mickey Mouse would be. Does your character have hair? Would you say Mickey Mouse has hair? Like, yeah, he doesn't have like human hair, right? He's a mouse, but I don't think that's what they're asking, right?
I mean, he has fur, but I don't think that's
all right. Thumbs up for yes. No. I guess don't know, probably. What do you guys say? I'm going to let you guys vote together. And it's okay if we mess up. It usually figures it out.
I'd say no. But
so one for no. Jenny, Andy?
Yeah, I should say no.
No?
Fine.
Okay, we'll go with no. Yeah, that one's debatable, right? Is your character originally from a video game? No, it's not originally from a video game. Character wear clothes? Yeah, he wears pants, right? Is your character linked with SpongeBob SquarePants? Okay, it's getting really specific now. So no, it is not. Is your character animal? Yeah, mouse. Okay. Character gender female? No, it's not female. Is your character like soybeans? I'm gonna say don't know. I'm gonna say don't know. Yeah, he could. I mean, who knows? Maybe Mickey Mouse canonically likes soybeans for some reason. Is your character a mouse? Okay, so I think it's starting to get an idea. So we'll say yes. Has your character been in the Mickey Mouse Club? That's okay. This one always messed. I think this one messed me up last time. Mickey Mouse Club. Does anyone know? That's not like the human character people.
I thought it was like when Justin Timberlake was on the Mickey Mouse Club.
Right. That's what I think. So I'm gonna say no. Right. Like it's not. I'm gonna say.
They asked if it was a mouse, and you said yes. So.
Yeah.
I feel like he must have been.
Okay, I'm gonna say yes then. Maybe if I'm wrong, maybe I'll go to did your characters live with both his parents? No. I don't think there's even have a clubhouse. Yeah? Okay. I see Lauren. Lauren's like really adamant. Okay, good. Out of Mickey Mouse. We may or may not have like answered some of those wrongs, but it figured it out. So the point here is that it made its decision, and it's actually really cool if you ever get the time just to play around with this. You can pick like literally anyone kind of deal, and it's a pretty good job these past like 10, 15 years. It has improved a lot. But this is essentially what a decision tree does. Essentially, it's saying yes or no questions and says, Like, is it this thing or is it that thing? And based on those decisions, it's going to break down into figuring out what specific classes it's going to be in. You can also, I'll kind of generally say, we'll use this analogy for classification, decision trees for classification, but you can use decision trees also do like aggression, which remember regression is not going to have classes like linear regression. But anyway, that's essentially what, what's it called? A decision tree kind of works through. So I kind of like that kind of show a little bit what that looks like. So kind of going more into like, okay, what is an actual decision tree? Remember, it's a supervised machine learning algorithm. So classification, it already has some data points that are already labeled as, you know, this class, or this class, or, you know, some value. It's basically a graph or pathway. So it's like a pathway of like trying to find, making those decisions. So it's a way for us to, like, the decision tree itself is the pathway to get to a decision. And so what's going to happen, essentially, we keep going through the data. So we start with all the data and we start like splitting it up into what we call partitions. And we partition those parts based on those features and some attribute to those features. So like some, this, for example, like what your age is, like, oh, if you're over 18, you're in this group. And if you're under 18, you're in this group. And essentially we keep splitting this up until we, you know, based on some hyperparameters. But the idea is like we keep splitting up until we basically can do a good classification. And so then what we do, we keep this tree and essentially say, okay, we trained it with all the data that we already know. And then we take some new data that we might not know. We don't know what the actual label is. We pass it through there and it spits out, say, oh, it's in class C or class A or whatever, based on those decisions. Okay. So I'll kind of put this little graphic here, and you can imagine like a fork in the road. Like essentially we're splitting off each part. Note that we technically don't have to do binary, but usually that's classically what we tend to do because it's just about the equivalent and it's a little more computationally efficient. So example of a decision tree. So this is kind of like an idea of like, you know, how this would apply. So imagine you have like this like little table of like work status, age, and favorite website. And your goal is like, hey, I want to know whose favorite website based on certain attributes. So you can see here like student, young, working old, working young, student young, student young. So really, really simple little table here. But you can kind of imagine where this might be used, something like this. So based on this table, if someone is a young worker, what websites would they recommend? So the way you could do that, well, I'll let you guys kind of decide. Like looking on this table here, if someone's a young worker.
B.
B, right? And you can probably see that, right, Lauren, is probably from like this table. Here's a young working person, and they both choose B. So that makes it pretty simple, right? What if someone's an old worker in this case?
C.
C, right? So these are pretty simple ones, but you can see like, you know, maybe it gets a little more complicated where maybe not everyone who's an old worker will always choose C, right? If we had more tables and stuff, but if the majority chose C, then we'd probably feel pretty confident. Or if there was more features, we could split them across and kind of get more details on this part. Okay, and that's essentially what a decision tree is going to do, essentially try to split it up based on these features. So here's kind of like me just writing out the overall steps of what a decision tree looks like. So essentially there are features and a target. So remember the target's going to be what class the data point is. Okay. And remember for regression, just think of like regression, what the target would be. It's also like would be like a value, but we're going to focus on classification. So essentially what we do, we take the whole data set and we make a decision, right? We split it based on some metric using the features. So we say, okay, taking this feature, like say work status, okay. Whatever, like, you know, like, oh, we're going to have all the students go over here and then everyone else on the right side. And we split those groups up, okay? Or we might say, okay, based on your age, we'll split the age to this side or this side, you know, going through. And essentially what we do, we split those into partitions and we just continue to do that for each group. So we split it from like, let's say students and workers, and then we split up from the students and workers again. So the way this usually is kind of shown, I'm gonna use a different color than that lime green. What this usually shows, like if you start off with all the data on top here and you split it up, like you can imagine going like this, and all this data right here is like, okay, let's say it's student, let's put Stu, and this is like a worker, let's put work. This means that, oh, we have all the students on one side, all the workers on another side, and then we would split this up again. It's like, okay, this is like the young, so the young, and this is old. And this would split up from young and old. Note that in this case, we only have two features and one target. This technically doesn't have to be the same feature when it splits off. It might make sense, let's say we have like a fourth or a third target. Let's say target, or is not target, third feature. Let's call it just like feature 3. this could split up like, oh, this is going to split up by age, but this one's going to split up by feature 3. So it doesn't have to go in the same order. It just has to partition. And we'll talk about how we make those decisions. Okay. But essentially the idea here is that we'll split up the data. So then that way you have just the young students, just the old students, just the young workers, just the old workers in each separate group. Okay. And this is usually how it's kind of drawn out, where you can imagine each of these boxes contain the data where it contains these people. Makes sense. If we had something that was more like a continuous value, so if we had something like, instead of age, like young, old, it was an age like a number of years, all that would be different would be say if it's greater than or less than. So it's like, oh, if someone is, their age is less than 18, we call, we'll split it off to this side. And we can determine this threshold and say, oh, we'll split it on this side. And that means everyone who's under 18, everyone who's over 18. Okay, makes sense? Awesome. So we'll move on to a little bit what this looks like. Oh, I kind of forgot to mention is that we also have a stopping condition. So we could technically keep splitting this up on all the different features. However, we usually have a stopping condition so it doesn't go all the way down with every single feature. And usually that means something along the lines like how many data points we have to have in the final like group, that final partition, or how many layers deep. There's a few other things we can do, but these are the typical ones. And so the reason, well, let me ask you guys, why would we want to have a stopping condition? Why wouldn't we want it to try out using all the features?
To avoid overfitting.
Yeah, basically, right? If we make it too specific, we might find patterns that don't really exist. In fact, you might actually find that there's no, let's say we had like 10 features, we have no person or data point that actually is all like very specific, parts of those features. So like, oh, for feature 1, they're A, and feature 2, they're A, and feature 3, they're A, and feature 4, they're A, and then going all the way through, you might not have any points. So it makes sense for us to stop there. Otherwise, we might find patterns that don't actually make sense or at least exist. One quick note though, is a greedy search. So basically the idea here is the decision tree will always make what they call a greedy decision, basically makes the most optimal decision. Okay, and so it doesn't always lead to the most optimal solution. So you can kind of imagine is that like, I'm trying to think of a good example, is if you had a choice, like say you had like, like team captains, right? It's like if you had like Captain A and Captain B, and they have to choose, different players on their team. They want to choose probably like the best player, right? Or something like that. But maybe if they choose more moderate players, that would be better, overall team. But if they pick just the best player at first, they're just picking like the most optimal like person in that certain situation where they pick the best one. That's essentially what a decision tree. So note that just because it's making the most, the greediest decision doesn't actually mean it's going to be the optimal solution. This also means something about decision trees, which is a little bit different from some of the other stuff we've seen before for some certain statistical learning, is that it's deterministic, which means if you have the same data and you have the same hyperparameters, which we'll talk about, but basically have the same criteria for the decision tree will always produce the same exact like structure. It won't be different. So there's no probability built into this. Okay, so does that make sense? Cool. All right, so any questions about this stuff, kind of overall view of decision tree? Cool. Right. This leads us into a little bit of exercise, right? So what we're going to do is we're going to make some decisions. So I actually went ahead, I'm going to go ahead and plot out some data for 2 different classes. I think it's gray and red, we'll see. And what we're going to do is try to make a decision to separate them out. And we'll see like what this looks like. And this is basically how these decision trees will kind of like function. Note that this is just extra code. You can kind of go through it, but I won't explain exactly how this goes through. I'm just generating some more or less random code with certain criteria. And I'm also creating this helper line right here. So later on, we're going to show where to split the data so we can visually see where that split happens. So let's see what this data looks like. And there you go. So you can see here, we want all the red and all the gray. We want to separate, it's like, okay, based on X1 or X2. So this is X1 feature, X2 feature. And you can think of the target is what class they're in, which is either gray or red. We want basically say, okay, we want to be able to determine based on X1 and X2, what group they're in. Okay. So you can probably see already like how you would probably draw your line if you were to essentially draw around here and say, okay, this is how we would determine if you're on, like, let's say, I'm just going to draw this out. Oops. No. wrong drawing tool. You can imagine I can draw a line like this right here. And I can basically say, if I could somehow figure out what this line is, I can say, okay, everyone who is underneath this line is gray, and everyone above this line would be red. So what our decision tree is going to try to do, well, what we're going to do, which is going to basically build our decision tree, is try to build up this line through steps, through an algorithm. Okay. So it sounds a lot more complicated than it really is. So first, we're going to do our first step. And this is essentially exactly what a decision tree does. Says, all right, looking at the example above, would a vertical or horizontal cut be better to split the classes? So when I say which one's going to be better, what I mean by is if I go ahead and take and make a line through this, let's say I make a line like right here versus like right here, what's going to separate better? So you can see well, we still have some mistakes. Like for example, this is all red, but you can see, oh, we have more actually pretty decent amount, we split it pretty decently. But this one over here is oh, we have almost all red on this side, but we made a lot of mistakes over here. So we want to set what's the best cut we should do. And then also we say what threshold. So where do we make the cut? Do we make it, if you're making a vertical cut like this, do we make it at X5, X4, X3, X2, X1, or if you're making a horizontal, do we do it at 1, 2, 3, 4, or 5? So looking at this thing, where would you guys think would be the best cut? Horizontal or vertical cut?
Vertical.
So vertical, so going up and down like this. And then Lauren, do you have an idea of where you would want to make that cut? What value?
Yeah, at 5. X1.
Right, cool. Yeah, I see Andy doing 5. Awesome. And Lauren 5. Okay. So we do something like this. So something like this, right? Yeah, and I would argue that looks pretty good. That seems to be separate. We're still gonna make some mistakes because we're only making one line, but I think that's a lot better than our best scenario with making a horizontal cut. You can kind of see if I make maybe at 7, right, or at 1, it wouldn't perform as well. Versus we got most of the gray over here and most of the reds on this side, especially the reds. Cool. So we'll go ahead, put this in the code. So our threshold, our direction. So if we go and test this out and we can actually see where this plot would look like, and you can see that's where our line would be. And we can see our solution is right, okay? Vertical and what's it, the threshold of 5, okay? So that was our first decision. So okay, cool, we made our decision, but you can see it's not perfect, right? We still have some mistakes on the left and the right, okay? So the next question is, what's splitting it further? What would be the next line threshold? Would we cut vertical, horizontal, and then where would we do that?
How about a horizontal line at 7?
Yeah, so let's try a horizontal line at 7, right? So that would look something like right here. And I think that looks pretty good because that would split across all the red right here. If we split this right here, it doesn't really matter. We'd say, oh, both sides are red. Or we might say the top is red and maybe there's some mix over here. So if we do this guy, you can see that's what it looks like right here. And I went ahead and you could draw this line completely across, but we can pretty much say, we're really trying to split off this left side here. Say, okay, now we have just red here, just gray. Then we have a mix on this side. Okay. And I would say, again, that looks what I would agree with you guys. It gives the most. We could have split it somewhere else, right? Where would be the other place we could have split it for a horizontal line?
Around 1.
Yeah, 1. And I would say that's not the best split right now, right? If we're gonna say, what's the best one in this moment, it really would be this part because it separates the most, gray and red versus right here. Yeah, it kind of helps, but doesn't really fix that many more mistakes. So the last one, as we can probably guess, is going to be where's our last line gonna go? And like you guys said, horizontal line, a vertical one, or at, did I put vertical right there? No, I did horizontal, okay. Horizontal at threshold 1. And essentially what we're doing here, and you'll see that right here, is essentially what a decision tree really does, is that it says, okay, let me just say, where's the best place to split each time? And you can kind of imagine is that on our very first try up here, we said, okay, we have all of this data. Where's the best place to split? Horizontal or vertical and what threshold? And it goes, okay, well, vertical makes the most sense and we have 2 partitions. Then essentially what it says, okay, between the 2 different partitions, which can benefit the most? The left side or the right side? And you say, oh, the left side benefits the most, and we should make a horizontal cut. So you can see here, That's what we did here. And then it's like, okay, this looks pretty good on each partition. This is completely classified. This is completely classified. What about the right side? What like, it's like, where can we make the cut to make the best decision? And that's where we get this last part. So essentially, this is what a decision tree would more or less kind of come across, considering there's only 2 features. So relatively simple. But what's kind of nice is that decision trees can work on many, many features. And remember, many features means many dimensions. So that's one of the reasons why I didn't only use 2 features, is that if I had more than 2 features, we'd have to have 3 dimensions or 4 dimensions or 5, which is a little tough to kind of draw out and visualize. So I think this worked out really well. Cool. Any questions on kind of this procedure and how it relates to decision trees? Cool. You guys are already masters at this. Okay, cool. So I like to show this little visual example. So this is not for me, but it's actually referenced in the curriculum. I don't know if anyone's came across this already. Cool. So I kind of just go through a little bit. If you haven't already like read through it, it's a great visualization of like, kind of like the data science process, and then it kind of shows like a decision tree. So I'm gonna skip over parts. So just know it's kind of doing some first initial splitting, but I think what we're going to do here is they're going to create a machine learning model to distinguish which homes are in New York and which homes are in San Francisco. So classification. And there's some features. I think they have things like number of bedrooms. I'm just going to scroll through this really quickly. There we go. So you can see like elevation, year built, bathrooms, bedrooms, price, and square footage. So they're basically doing a quick, kind of say what features are available, what things look good. And then we say, okay, just a machine learning algorithm, and they're actually using a decision tree. So this shows a really great example of this. So essentially we take all the data points, we say, okay, here, in this case, they're just showing all like histogram stuff. And I think, okay, this is when they make their first decision. And they say, okay, they're basically on the decision tree says, what's going to give us the most bang for the buck the very first try? We're not going to be able to make a single cut and split everything from New York and San Francisco, but we can maybe make a decent cut. And you can kind of see already, I think this histogram is of like elevation. You can probably see, say, if I make a cut right here, we pretty much like have all of New York, on the right side and all of San Francisco on the left side. But that's just with one feature. So that's what they're going to do here, I believe. So they split it up basically on, it's splitting on this elevation part. So you see right at that 242.8 feet above sea level. There's, all right, everyone to the left, we're split it off to one partition, and then everyone to the right here is San Francisco. So you can see here is that we get all of San Francisco by itself, but we still have a mixture of San Francisco and New York on the left side. So then we can go off to the next, what's it called? The next like feature. So it's kind of just showing like, oh, false positives and stuff like this. And it says, where's the best split? So it's trying to figure out like where would be the best one to kind of like get the most, what's it called? Like most bang for your buck. Okay. And you can see it actually decides in this case, not to be perfectly put it on here because there's still most of them on New York on this side right here. I'm sorry, most of them are San Francisco on this right side, even though there's a couple of mistakes, and that's okay. So we want to get the most bang for your buck on that one cut. So then essentially we keep repeating this with all the different features. So this is my favorite part, is actually like they saw growing the tree. Essentially we start with this elevation. So you can see on the left side here, that's that little threshold. Left will be on this partition, right will be on this side. And you can see probably after one more split on that right side, we'll probably get pretty close to getting all San Francisco. And you can see here, we split one more part, in this case, the price. And we can see we've got some data points over here, mostly New York. And then most of them over here are San Francisco with a couple of mistakes. And note on the left side here, that first partition on the left side, we split it by price per square footage. And you can see kind of this distribution, and that threshold right here would make the most sense. Okay, and so that's how we kind of go through and just keep going through the different features, splitting up those different partitions. And you can see here is that already after splitting from elevation, price, and square footage, we can actually get just New York, just San Francisco by itself. And you can see over here, we're pretty close on this side because price per square foot is already just New York. Same thing for this elevation, price square footage, price square foot, and square foot over here. Okay, so you can see is like we can get better and better by basically keep splitting it until essentially we have all, in this case, only New York or only San Francisco for each of these partitions. Okay, make sense? I know that it says 100% accurate. Okay, now I can't remember if this one talks about it, but one thing that could be an issue is that this can overfit. If we kept splitting, hopefully we eventually be able to figure out each individual part, but we might find patterns. For example, if you get to the point where there's only one member per that split, it might be kind of like, well, that might just be pure chance. But in this case, it looks like 100% accurate. So this is us training the data. So now we actually design this tree from the data we already have labeled. Then what you do, you want to go ahead and test it out. Say, hey, how well did it perform on data that it hasn't seen yet? And so you can basically imagine your decision tree as kind of these splits. You ever have those little things where you drop the ball and they can go either left or right. I think I showed this like once in statistical distributions, right? So like that's kind of like what's going on here. So you can imagine dropping the ball and it goes left or right, kind of going through, depending if, you know, elevation's less than 91.9 feet, our price per square foot is 106.5 square feet, and all that stuff. So essentially what we can do, we can go ahead and take some test data and we can go and drop it out. So this is data that is never seen before. And that's what these little balls right here represent, you know, either San Francisco in green or New York in blue, and see where it would fall on those parts. And we want to see how well it performs. And you can see in this case, I think they actually literally use the training data to go through here, which of course we saw already gives 100% accuracy. That doesn't really help us. So they say, okay, let's go and try to use test data that we haven't seen before and see how well it performs. And you can see there's already a few of them that make a mistake. These are the little hollow ones right here. And you can see here, it's going to make a few mistakes. In this case, on the testing data, it gets about 89.7 accuracy. So it's a little bit of overfitting. So they might need to like kind of stop a little bit further here. They might have made a few too many errors, but you can kind of see it's like, okay, we now have this accuracy here and we can kind of test it out. So remember the decision tree itself is this thing, which we grow from the original data. Does that make sense? Cool.
Why would you say that there's overfitting? Because we're 10% less than 100.
Right. Yeah. So this is, so we can see our, when our overfitting, we can say overfitting tends to happen when our training accuracy is really, really good, but our test or our validation, I don't like calling it test, I like call it validation. Our validation accuracy is lower than that. So what might happen, you can kind of imagine, and this, I'm going to keep showing this graph because it's a really typical one we'll talk about for overfitting stuff like this. If you imagine on this x-axis being like complexity of the model. So, and by complexity, that just means more branches, or later on, we'll talk about it like neural networks, like, you know, more neurons and more connections stuff. Basically, the more complex your model is, what will happen, and this, imagine this is the error. You can think of error or loss, right? It doesn't really matter. But the point is like mistakes you make. What will happen is your training data, I'm going to draw this in like, I'll draw in blue. Your training data, well, at first with a very low complexity, is basically going to have really high errors, right? If you had only one split, it's going to make a whole bunch of errors. But as you make it more and more complex on this training and we train it on this training data, we'll find basically makes smaller and smaller errors. In fact, it might actually reach a point where it just plateaus, right? Or it'll get down to zero. In this case, it went down to zero, basically no errors, right? And that means higher and higher complexity. However, if we compared, like say, okay, every time we made these different, I'm just kind of draw these little points. If you imagine at every point right here, so like every different complex model, we test this like, okay, let me go and test the model after training on new testing data. And it performs this well. Like it's like, okay, like it didn't perform as well as the training data, but you would expect that. But if you notice, if you kept doing this for each complex model, what would happen is this testing data, this testing error would still kind of fall down, right? As we get more and more complex, which is what we want. But at a certain point, what might happen is that it doesn't get, you can see it's like dropping very significantly for training, and for testing, it doesn't tend to do it. And then all of a sudden, what will happen, well, not all of a sudden, but it'll tend to start going up. So as we get more and more complex, this data points will actually get up like this, where the error actually increases now. And essentially, if I were to connect these lines, you see this kind of like little inflection point right here, where it's like, oh, like it's now suddenly going up. And then we say if you're in this area right here, where it's complex and the error is actually going up for the testing, or I should say validation, this is saying, hey, we're starting to overfit. Essentially, we're getting really confident in our training, but it turns out it doesn't generalize well to the testing. So generally, like, as, for example, if you ever get 100% accuracy for a training model, you should kind of like say, let's double check if we can maybe sacrifice some accuracy for less complexity, which might actually perform better on your test. Because really we want a model that fits like about like right here. Right? So maybe not as complex. It's actually going to do a little bit worse on the training, but that's okay because we don't care about the training. We just use that to grow our tree or whatever model we're doing. We really want to care about the validation or test set. Make sense? Awesome. Yeah, and this, I think this graph right here, you'll see this very commonly. It's drawn different ways depending on if you're talking about loss or error or complexity or other hyperparameters. But this general model is true in sense, or this general plot is generally true. As we increase more complexity, your training error will get lower, but your validation and test error will tend to eventually start going up because essentially it is. If you are right here though, if you stop this complexity and you stop at this graph right here, you can kind of see it going down. It hasn't stopped going down, it hasn't gone back up. it probably means that your model's still too simple. Like it might be good enough, but you can probably make it a little bit more complexity. And there's a few ways, either more splits and stuff like for decision trees, and for other models, that means other different hyperparameter tuning. But that's kind of like the suggestion here. Okay, cool. Good question though. All right, so that's kind of like our intro to decision trees. Again, great. Read this through if you haven't already, because that's really great how they kind of explain through a lot of other stuff, some great visualizations and stuff. Okay, so one part of this is we kind of said like, okay, decision trees make decisions to make these splits, but we really didn't say like, how does it make these decisions? Like I kind of vaguely said it makes the best decision, but we haven't talked about like, how does that determined? And so that's what we'll talk about next, which is basically going to be about information.